Today, we're pulling back the curtain on the invisible architecture that powers, well, everything in our digital world. We are talking about system design, which is basically the master blueprint that makes your social media feed, your online shopping, all of it just work. So let's trace the journey of a single click and really uncover the blueprint that makes it all possible. It's something we do probably 100 turns a day without even thinking about it. You click a link, and like magic, a web page just appears. But that one simple action, it kicks off this incredible high-speed journey across the entire globe. So what is actually happening in those few seconds between your click and the page loading? Come on, let's follow the request. Okay, so at the heart of all this is system design. The best way to think of it is like the master plan for a massive digital city. It's not about writing the code itself, but about deciding how all the different pieces, the servers, the databases, the services, are going to work together. And the goal? It's to build something that can handle millions and millions of users without even breaking a sweat, making sure it's both super fast and super dependable. So our journey begins with a really simple translation. Before your browser can even think about finding a website, it needs to translate that human-friendly name you typed in into a machine-friendly address. This is the first absolutely critical step, going from a name to a number. This whole translation thing is handled by the Domain Name System, or DNS. And honestly, the best way to think about it is as the internet's phone book. It's a perfect analogy, right? You don't memorize your friends' phone numbers, you just look up their name. Well, DNS does the exact same thing for websites. It takes a simple name like example.com and turns it into a numerical IP address that computers use to find each other. Now, this lookup isn't just one step. It's this incredibly fast chain of questions. First, your computer asks a local resolver, which then goes on a little hunt. It asks a root server, hey, where are the .com servers? Then it goes to the .com server and asks, okay, where is the server for example.com? And finally, that server, the authoritative one, gives the final IP address. It sounds kind of complicated, but this all happens in milliseconds, mostly because of some really clever caching at every single step. So the IP address we get from DNS, that's a public IP. Think of it like the street address of a building, totally visible to the entire internet. Now that's really different from a private IP, which is more like an apartment number inside that building. Private IPs are for all the devices on your local network, like your laptop, your printer, so they can all talk to each other without being exposed to the whole world. Okay, we've got the public IP address. Our request has officially arrived at the right location. But, it doesn't just waltz in the front door. These huge systems have gatekeepers, and they're there to manage the absolute flood of incoming traffic. Our little request has to get past them first. The very first gatekeeper is usually a reverse proxy. It's a server that stands right between the internet and the application's actual servers, acting as the main front door for all traffic. And this setup is genius for security because it completely hides the internal network. Plus, it boosts performance by handling things like encryption and caching, which frees up the backend servers to just focus on their main job. A lot of the time, this reverse proxy also works as a load balancer. I mean, think about it. A popular service can't run on just one server. It would get totally overwhelmed in an instant. Load balancing is the art of spreading all those incoming requests across a whole fleet of servers. This is what keeps any single machine from becoming a point of failure and makes sure the whole system stays up and running. So the whole goal of a load balancer is to get a perfectly even distribution of traffic. It might just send requests in a simple round-robin style. You get one, you get one, you get one. Or it could use more complex logic, like sending you to the server that's least busy. But either way, the outcome is the same, a balanced, stable, and highly available system. All right, our request made it. It's past the gatekeepers and it's been assigned to a specific server. So now we're going inside the system. Let's call it the digital factory, where the real work starts. The fundamental idea here is the client-server model. It's a simple concept, but it's incredibly powerful. Your device, the client, makes a request. The system's application server gets that request, does some work, maybe it fetches data from a database, and then sends a response back. This simple request-response cycle is literally the heartbeat of the modern web. Now, in today's really complex systems, there's usually another layer of traffic management inside, the API gateway. So if the reverse proxy is the main front door for traffic coming from the internet, the API gateway is like the factory floor manager, directing traffic within the system. It takes a request and routes it to the correct specialized service, one for user profiles, another for payments. You get the idea. Now, here's a really critical design choice. Are the servers going to be stateless or stateful? A stateless server treats every single request as brand new. It has zero memory of past interactions. This makes scaling up incredibly easy. Any server can handle any request. A stateful server, on the other hand, remembers things, like what's in your shopping cart. And while that's convenient, it makes scaling way harder, because a user's requests might need to keep going back to the exact same server that's holding their data. So we've seen the individual parts, but how do they all fit together into a coherent system? Well, the overall blueprint is defined by its architecture. Let's take a look at the two big approaches. On one side, you've got the monolithic architecture. Think of it like an all-in-one appliance. Everything is in one big code base. This is usually the best way to start a new project because it's so fast and simple to build. But as it gets bigger, it can become a real monster to update. On the other side, you have microservices, which is like building with Legos. The application is broken down into tiny independent services. This gives you amazing scale and flexibility, but it also adds a ton of hidden complexity because now you have to manage hundreds of these little services all talking to each other. And let me tell you, this choice is monumental. It's not just some technical detail. It dictates the entire workflow of the engineering team. It determines how fast you can roll out new features, how you handle massive spikes in traffic, and whether one little bug could bring down your entire application. This one decision has massive, long-lasting consequences. And our request has been processed. The server has done its job. It's assembled the web page or the data, whatever it is we asked for. Now it's time for the final leg of the journey, getting that response back to our browser as fast as humanly or, I guess, digitally possible. This is where the Content Delivery Network, or CDN, becomes the hero. Instead of sending everything from the main server, which could be thousands of miles away, a CDN stores copies of static files like images and videos on servers all around the world. So when you request that content, it's delivered from the server that's physically closest to you. It's basically the express lane of the internet, and it dramatically cuts down on load times. And there you have it. From a simple DNS lookup to navigating proxies and load balancers, from all the processing on the server to that final, speedy delivery by a CDN, that entire complex journey is a hidden, high-speed ballet of technology. It's this intricate dance, and system design is the choreographer making it all happen. The blueprints we've talked about today power the internet as we know it. But as we all know, technology never ever stands still. With billions more devices coming online and data growing at a rate we can barely imagine, the designs we use now are going to be pushed to their absolute limits. So the real question is, what does that next master blueprint look like? How are we going to design systems for a future that's even more connected, more real-time, and more data-intensive than anything we have today? That's the challenge waiting for us.